Welcome back, focused learners. Today, we're flying at maximum altitude. We are diving deep into an explainer that is absolutely vital for mastering your IGCSE 0478 computer science concepts. We're going to embark on what I like to call the software architect's journey. Think of this as your advanced aerial combat strategy for tackling the toughest exam questions. This is our strategic blueprint for exam mastery, taking you from the very first spark of a program concept all the way through to rigorous testing and validation. We're going to look at actual source materials, standard algorithms, and the exact logic structures you need to know to secure those top marks.
Okay, let's dive straight into our flight plan for today. 1. The blueprint. 2. Visual logic. 3. Control structures. 4. Searching and sorting. 5. Validation versus verification. And finally, 6. Testing and trace tables.
Let's kick things off with Section 1, the blueprint.
So before we even think about writing a single line of code, we have to enter the first critical phase, learning how to actually think like a computer scientist. An algorithm isn't just code, right? It's a meticulously planned solution. And to build that solution, we rely on two massive fundamental tools, abstraction and decomposition. Now, abstraction is all about focus. It's the process of filtering out and completely ignoring the characteristics of a problem that just don't matter to our specific solution. We're stripping away the noise. Imagine building a flight simulator. You need the physics of the plane, but you don't need to simulate the exact stitching on the pilot's seat. That's abstraction. Then comes decomposition. This is where we take our complex, overwhelming problem and break it down into much smaller, highly manageable parts. It's how we conquer the chaos. Once we decompose the problem, we use structure diagrams to visualize our entire plan. We use a method called top-down design. Imagine a hierarchical tree. At the very top level, we have the main computer system. Then, step 2, we break that massive system into subsystems. And we don't stop there. We keep breaking those subsystems down further and further. We do this until we hit step 3, where we have a complete diagrammatic description of the solution. Each lower level gives a much more detailed description of the system. It's literally the ultimate blueprint for your software.
Moving right along to Section 2, visual logic.
Now that we have our problem broken down into manageable subsystems, we need a reliable way to map out the exact sequence of actions. We are transitioning from raw human thoughts into structured universal languages using a standard algorithm flowchart. And this brilliantly illustrates how we do it. Notice how the flow lines dictate the exact directional path of our program. We start at the top, move through input parallelograms, like asking, "How many guesses would you like?" and then, "Please enter your guess." And then we hit those absolutely crucial decision diamonds. Notice the logic happening here. We check if the guess matches the target word. If it doesn't, we subtract 1 from our total guesses and loop right back around. It's an elegant visual way to debug our thoughts before typing any syntax. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, back to the logic. Loops can be incredibly tricky, and their structure matters immensely for your exam strategy. Let's look at 2 different ways to write a flowchart loop. Say, for a program meant to output the names of 20 students stored in an array. On one side, we have a pre-condition loop. Here, the loop counter is tested at the very start of the loop. If the condition isn't met immediately, the loop might literally never run. On the other side, we have a post-condition loop. In this scenario, the logic executes first, and the loop counter is tested at the end of the loop. This guarantees the code runs at least one single time. Understanding this subtle visual difference is an absolute game changer when you're mastering iterative logic for the exam.
Which brings us to Section 3, control structures.
Flowcharts are fantastic for visual planning, but eventually we have to write this out using pseudocode to actually build our software architecture. There are 3 core types of pseudocode statements you absolutely must know inside and out. First, assignment. This is simply assigning a value to a variable or an array item. Easy enough. Second, conditional statements, like your if, then, and else. This is how our code evaluates different conditions. For example, outputting a specific welcome message if a user inputs the name Alice, or a generic rejection message otherwise. And third, iterative statements. These are your for, while, and repeat loops, which we use to efficiently iterate through data, just like processing those 20 students we mentioned earlier.
Speaking of arrays and large sets of data, you might be wondering, what happens when our program scales up? If we have an array of 1,000 students, how do we efficiently find one specific student? Or how do we organize their exam marks from highest to lowest? This is exactly where we need an advanced standard toolkit.
Section 4, searching and sorting.
The Cambridge curriculum tests very specific standard methods to handle lists of data, and you need to know exactly how to implement them in your algorithms. Before we even get to sorting, let's look at some basic methods of solution. Counting is just keeping a record of the number of times an action occurs. Think of adding a new value every time an action happens, like awarding a mark to each student. Totaling is summing all those values up. If we take that total and divide it by the number of times the action occurred, boom, we get our average. And of course, your algorithms will frequently need to evaluate data to find the largest, the maximum, and the smallest, the minimum values. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, so the crucial point here is knowing the difference between finding an item and organizing items. If you need to look for a specific item in a list, you use a search. The standard method you need to know for IGCSE computer science is the linear search. This is where your algorithm inspects each item in the list in turn, from the very first to the very last, to see if it's the required one. It's like checking every book on a shelf one by one. On the other hand, to put a list in order, like sorting 10 student names into ascending alphabetical order, you use a bubble sort algorithm. This method repeatedly steps through the list, compares adjacent elements, and swaps them if they are in the wrong order.
Next up, Section 5, Validation versus Verification. Once we've built the logic to process, search, and sort our data, we have to pivot to our quality control phase. Listen, the smartest algorithm in the world will completely crash if you feed it garbage data. We have to guard our program. And this right here is where students often lose marks, confusing validation with verification. They are absolutely not the same thing. Validation is an automated check built right into your code. It checks if the data input into the computer program is reasonable and meets given criteria. For example, checking if a temperature entered is actually a number and not a letter. Verification, however, happens mostly on the human side. It's checking if the data entered perfectly matches the original source data, usually achieved by double entry or a visual check by the user on the screen. So validation checks the logic, verification checks the accuracy.
Finally, Section 6, Testing and Trace Tables.
So, we've designed the blueprint, we've mapped the flowcharts, written the pseudocode, and added our validation checks. Now we enter the final phase where we execute dry runs to guarantee our software architecture actually works exactly as intended under every possible circumstance. To properly test an algorithm, you can't just use random numbers. You must systematically use 4 specific categories of test data. Normal data is your standard expected input. Erroneous data is data that should be completely rejected, like typing a letter when a number is asked for. Extreme data tests the very edges of the acceptable limits, and boundary data tests the exact cutoff points. For example, if you need to check that a whole number is less than 100, your boundary data would specifically test the numbers 99 and 100 to ensure that less than logic triggers perfectly. Let's move to a real example and see how this builds in a trace table. A trace table allows us to manually track the values of variables as a program runs, a process called a dry run. Look at this execution matrix. We start with variables w at 0, x at 0, y at 100, and z at 0. When our first test data mark of 78 is input, we evaluate it line by line. Since 78 is greater than x's current value of 0, x updates to 78. Since 78 is less than y's 100, y updates to 78. Z totals the marks and w acts as a counter. Then we input the next test data, 34, and all the variables update again based on the conditions. Following this manual trace step by step is the absolute best way to catch logic errors before they become a real-world problem.
Now, let's put this into practice on an algorithm that is fundamentally broken. I want you to look closely at this flowchart. It's supposed to check if a temperature input is between 20 and 30 degrees. But look at the decision diamonds. First, it asks, is T less than 30? If yes, it immediately outputs too low. Wait, if the temperature is 25, it is indeed less than 30, so it outputs too low, even though 25 is perfectly within our 20 to 30 range. The logic path for is T greater than 20 is also entirely disconnected from a proper continuous flow. This right here is exactly why we trace. It highlights exact structural flaws in our condition testing that we might otherwise gloss over.
Which brings us to our final provocative thought for this explainer. You can decompose a problem perfectly, you can write beautiful iterative pseudocode loops.
and your flowchart might look like a total work of art. But if your flowchart logic relies on unverified inputs and your test data lacks extreme boundaries, did you truly solve the problem? The answer is no. A robust algorithm isn't just about making things work, it's about anticipating exactly how they might break. Keep that mindset as you tackle your next set of practice algorithms. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. So, here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_ in GCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_ in GCSE and clip that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're currently facing. Our team responds to every single comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here. Keep building that brilliant logic, and I'll see you next time.